Welcome, students, to your last unit. Once you are done with chapter 10.8, which is this one, you are done with the Precalculus course. Yay! And I'm done making videos. Teaching live is a lot more fun and a lot more interesting. But this has been cool. It's been a cool experience. I hope you guys have enjoyed it enough, and I hope it's been good for you. So congratulations on getting to the end, and just one more obstacle. And this section is an easy one. It's very easy because it's very introductory in nature. You're just kind of getting your feet wet and trying to get a basic understanding of what polar graphs look like. So that's what we're going to do. We are going to be graphing some equations on a polar plane, like this one. For example, sketch the graph of the polar equation r equals 2 times the sine of theta. And to do that, we're going to make a table. We're going to make a table for 2 of them. And then when you usually graph these, we're just going to go to Desmos and punch it in. But we're not going to do that right away because you need to have some sense of where these numbers and why these shapes are happening. So to get some sense of what's going on, we're going to do 2 of them by hand. All right, so here we go. Have the unit circle by your side. And let's start. So let's plug in 0 for theta, and we get 2 times the sine of 0. Now the sine of 0 is 0, so 2 times 0 is 0. You'll get the same thing, of course, at 360 degrees. At 180 degrees, the sine is also 0, so put that one there. I like to do the easy ones first. So for example, I'm going to skip over to 90 right now, because at 90 degrees, I know that the sine is 1, and 2 times 1 is 2. At 270 degrees, I know the sine is -1, so 2 times -1 is -2. Other easy ones, 30 degrees. 30 degrees is easy for the sine, it's just a half. So 2 times a half is 1. And 150 degrees is also a half. So 2 times a half is 1. 210 and 330, you can look at unit circle, that's where it's -half. So 2 times -half is -1 and -1. Now the only numbers that are irrational are 60 degrees and its brothers. So the sine of 60 degrees is √3 over 2. So if I do 2 times √3 over 2, I'm of course going to get √3. And √3 is about 1.7. 120 degrees is also going to be √3, and these guys will be -√3. And of course that's about 1.7 and -1.7. So let's go ahead and graph this now and see what we get. Last lesson you learned how to plot points, so let's plot. So 0, 0 is right here. 30 degrees and 1 is here. 60 degrees and 1.7 is here. 90 degrees and 2. 120 and 1.7. 150 and 1. What we actually have here, and if we had more points, you could see it even better, is we have a circle. That's all it is. This is making a circle so far. And let's see what will happen as we keep on going. But so far we got a circle. Okay, now let's plug in 210 is -1. I'm going to actually change colors for this. I'm going to go to green for the second part. So 210 is -1. So here's 210, and -1 is there. 240 is -1.7. So here's your 240, and -1.7 is here. 270 is -2. So 270 is here, and -2 is going to be up there. Uh-oh. You see what's happening? It's just going over it twice. So what this graph actually is, it is a graph of a circle, but it's actually going to trace it twice if you go all the way to 360 degrees. If you just go to 180, if you restrict your domain, you'll just get that one circle right there. So there's a circle. For this particular one, I would actually like to do this one little exercise with you. We're going to convert this to rectangular coordinates. And as I convert it to rectangular coordinates, I should get the equation of a circle that is slightly, well, let's not just slightly, let's be precise, where the center is moved up 1. So an equation of a circle where the center is moved up 1 and where the radius is also 1. I think you know what the equation is. That would be x squared plus y minus 1 squared equals 1. That's what I'm looking for. So let's see if we can do this. I hope you remember a few little tricks from last time, that to convert from polar to rectangular, you are going to use, oops, I forgot the r, y equals r times the sine of theta to get your y value. And I hope you also recall that x squared plus y squared equals r squared. So these are some of the conversion factors we used in chapter 10.7. So let's apply it to this guy. Let's see. I'm going to use this. And I know that if y equals r times the sine of theta, I can conclude that the sine of theta equals y divided by r. Fair enough? So let's go ahead and rewrite my equation as, hey, I forgot something, didn't I? I forgot the 2. There you go. Sorry about that. So r equals 2 times y over r. And I'm replacing y over r for the sine of theta because that's that. All right, let's multiply both sides by r. And now I have an r squared. So I can use this conversion to get rid of the r squared. So I got rid of the theta first, because I want x's and y's, not theta. And I'm getting rid of the r, because I don't want r, I want x and y. So I can have, instead of r squared, x squared plus y squared equals 2y. That doesn't look right. Let's keep going. So x squared plus y squared minus 2y equals 0. So what I can do here is I can complete the square. So this is my b term. Take half of -2, which is -1, and square it. So and add that to both sides. And then we can factor this. And as you can see, that is the equation in rectangular form. This is a circle that is moved up 1 and has a radius of 1. It's this, perfectly. Okay, let's do one more of these. So this one's a circle. It's kind of boring, but it was a good introduction. And we're going to do a second one that's going to be a little bit weirder. I told you right away, actually, in this little box, that the shape that we're about to make is called, it's in French, a limaçon. A limaçon in English? I don't know. In French, it's limaçon. And it's a goofy looking shape. So let's try it. Let's see what we get. Once again, let's just use a table to graph r equals 1 minus 2 times the cosine of theta. So let's start with the easy ones. I'm just going to kind of picture this in my head. This is the graph of the cosine. That's one cycle. My zeros happen right there at 90 degrees, which is pi over 2 because we're in radians, and at 3 pi over 2. So I'm going to start with those. So at pi over 2, I know the cosine is 0. So I get 1 minus 2 times 0, which is 1. And I get 1 there also. What else is easy? I know that at 0 and 2 pi, the value is 1. So 1 minus 2 times 1, that's going to be -1. Here and here. What else is easy? Oh, pi. Right there, it's -1. So 1 minus 2 times -1 is going to be it's going to be positive 3. And is there anything else that's easy? Oh, yeah. Where's the cosine of half? At pi over 3, the cosine is a half. So 1 minus 2 times a half, well, that's just going to give me 0. Where else is a cosine of half? Right over here. And so that also is going to be 0. Are there any other easy ones that we could do? Oh, yeah. Where is it negative half? So it's negative half right here at 2 pi over 3, aka 120 degrees. And if I plug in -1/2, this will give me 2 there and also 2 there. All right. These remaining guys are a little bit tougher. They are the cosine of pi over 6 or 30 degrees. That is your famous root 3 over 2, which is approximately 0.87 more or less. So if I plug that into here, and for all of these remaining guys, I kind of did the work ahead of time, but it's going to be -0.8, 2.8, 2.8, and negative 0.8. Now, the reason I didn't leave the answers exact radicals is because I have to graph it. And so I don't want to have to I don't want to have to graph root 3 over 2. I'd rather graph like, 0.87. So here we go. Let's graph them. So at 0, theta r is negative 1. So here's my 0, and negative 1 is going to be there. At pi over 6, which is 30 degrees, it's negative 0.8. So it's going to be there. At pi over 3, it is 0. So far, these are all curves, so it's curving like that. At pi over 2, it is 1. So now it's curving like this. At 2 pi over 3, it's 2. Seems to be getting bigger, like that. It's always a smooth curve. At 5 pi over 6, it's 2.8. And at pi, it is 3. So it's kind of like this seashell shape right here. And that's what we have so far. Now, the rest of it, I'm going to speed it up a little bit. But it's basically going to mimic what we just did. And it's going to come around like this, come back through here, and come back through there. So that is a goofy little loop-de-loop thing, which is called in French a limaçon, and in English a limacin or something like that. Kind of cool, huh? We're going to leave that right there. I just do want you to notice one little thing here. There's definitely some symmetry happening right here. Do you guys see that? So there's a very simple rule that simple cosine polar equations are always symmetrical over this axis right here. They're always symmetrical right there. And I'm going to take you back to the previous page because some very simple sine functions are always symmetric right there. So your sine graphs are symmetric this way, your cosine graphs are symmetric that way, vertically versus horizontally. So here are some basic rules for you, and we just observed it. So in terms of symmetry, if you have r equals f times the sine of theta, like r equals 3 times the sine of theta, it will have symmetry with respect to the line theta equals 90. In other words, this way. If you have a graph that has a cosine, its symmetry will be with respect to the polar axis. In other words, this way. And this g is just any number, like r equals, I don't know, negative 2 times the cosine of theta. Another thing it's nice to find is the maximum values and the minimum values. And I kind of modeled that when I went through the table. I said, okay, where is it 0? Where is it negative 1? Where is it positive 1? And if you find those points first, it really helps you graph these things. So that's what this is about. And these statements are fairly obvious. For a sine curve, for example, the maximum occurs at 90. And for the cosine, it occurs at 0. Now, where am I getting that? So the sine curve looks like this. Where's the maximum? For the cosine graph, which looks like this, where's the maximum? At 0. Now, if you have negative, of course, it's going to be opposite of that. For example, just with the sine, the negative sine curve looks like this, and the maximum occurs at 270. So these statements aren't anything too deep. It's just looking at these curves. All right, one last thing. The last thing, and the third learning target, and I know this is really small, but that's because we're about to go to Desmos, is that there are 3 kinds of graphs that you should be able to recognize. There are many, many kinds of polar graphs, but there are 3 that you should say, I know what that is. The first one is circles, and we'll go to Desmos and look at that in a second. The second one is the rose petals. And the third one is the hyperbolic spiral. There are many other kinds, but we're going to take a moment to kind of look at those and just play around a little bit. So join me and come on over to Desmos. All right, let's start with a circle. So we looked at this last time, but it's pretty simple. If you do r equals 2, you're going to get a circle. R equals 3 is a bigger circle. R equals 4 is a bigger circle. It is very easy to graph or to write the equation for a circle in polar coordinates. Now, what you should try is you should try to play around with these things and see what happens when you change things up a bit. Let's go to the second one. The rose petals are a lot of fun. This one's the rose petal. So these equations always look like this. R equals some number times the sine or the cosine of theta. So this first number in front decides how big it is. So see, that has a radius, I guess, of 1. If I make this 2, it has a radius of 2. If I make it 3, it has a radius of 3. If I make it 7, it has a radius of 7. I'll make it 4. This number in front of the theta changes the period, basically. So if I just have a 1, well, that's just a circle. So there's your 2 theta, 3 theta, 4 theta, 5 theta. Notice that when it's 5 theta, you see 5 petals, not 10. But when it's 6 theta, you see 12. Whenever you have an even number there, you see twice as many. That's because an odd number is actually tracing over itself twice, like it happened in that first graph we did. So anyways, these are rose petals. And what you can do, if you just want to play around with this, go ahead. See what happens if you put like a 2 minus in front of it. It doubles it. It gets like really weird and crazy and stuff like that. But I'll let you play around with that. The last one I want to show you about is the spiral. And this is called a hyperbolic spiral. And it's basically R equals some number divided by theta. So I put 5 there, but I mean, I could have put other things too, like, like 3, or maybe -3. Whoop, there it goes. Or I can make like a big number, like 30 instead. So basically, these are it's called a hyperbolic spiral, and it's something that you should be able to recognize. It has an asymptote. That's a question in your homework. Let's go back to, I'm just going to show you one more. Like if you want to get really creative, you can. This one, for example, has both a sine and a cosine in it. And if you want to put in a tangent, you can. There are an infinite number of possibilities. I Googled this. I just entered cool polar coordinate graphs. And look at all the stuff I got. I mean, you could go crazy with this. You can make a maple leaf, and it just goes on and on and on and on what the possibilities are. So I think that is all there is. In this homework assignment today, when you do the actual assignment, you are pretty much welcome to use Desmos. And the goal is not for you to become an expert at polar graphing, but the goal is for you to become acquainted with polar graphing. So that next year in calculus, when the teacher mentions polar graphing, and here is a polar graph, you're like, yeah, I know what we're talking about. All right. So happy summer, and thanks for hanging in there with me. And I'm sorry it didn't go as planned, but sometimes when life gives you lemons, you got to make lemonade. Mr. Peretti's out. Bye.